This box method allows us to see how multiplication and addition can interact with each other. And we can see physically how they interact, and if they physically interact in that way, they must algebraically interact in the same way. If I have 3 times 10 plus 2, well, I could do 10 plus 2 times 3, and that should be 36. Now I'm going to get an area of 36 regardless of whether I break it up in this 12 into 10 plus 2. And I can see that if I multiply 3 times 10, this portion is going to give me an area of 30. And I can also do that here. I can see that the length of 3 relates to a width of 10. So that 3 interacts with a 10 in multiplication. And we end up with times 30. We end up with 3 times 10 is 30. So that interaction of 3 and 10 gives us 30. But we also know that that length of 3, this length of 3 here, interacts with that width of 2. And so we need to make sure we show that. So the 3 must interact with that length of 2. And 3 times 2 gives us this area of 6. And we're going to add on, because between these two areas we need to add these areas together. We're going to add on a plus 6. And this confirms that, yeah, if we share or distribute this length of 3 with both these widths of 10 and 2, and we show that with this kind of looping thing, this is called distribution. I can see that I get these two areas of 30 plus 6, and I know that the area is conserved, and my answer must be the same as what I got before, which was 36. So 3 times 12 is 36. 3 times 10 plus 3 times 2 is also equal to 36. And we can distribute that length here because that length is shared here and here. And we show that with this distribution here and here. Now, we really wouldn't need to do that. There was no need to do this because we can just add 10 plus 2 and multiply it by 3. That would be much easier to do. So it would be unnecessary. In fact, we shouldn't do this. We should just do the brackets first and then multiply. When would we need to do something like this? Well, if I have a plus 2, a and 2 are different. This is counting a's, this is counting ones. We cannot combine things that are not the same. So in this case, we can't, although we want to do brackets first, we can't actually do this addition. So we have to leave it like that. But I have 3 groups of those things. Well, if I have 3 groups of a and 3 groups of plus 2, really I should have 3 a's and 6 ones. And we can see that if in our area model here, it's the same as this last problem. The only difference is we just, instead of 10, we now have an unknown a. And I can count those groups of a by distributing that 3 into my brackets. So that 3 interacts with this length, this width here of a. So it should just go 3 groups of a. Yeah, that makes sense. That 3 means 3 groups. And I have a in the brackets, I have 3 groups of a. If I think of this in terms of area, I have a length of 3, a width of a, that area must be 3a. Okay, that's perfectly consistent. I'll just keep this the same color. So I have 3 groups of a, gives me 3a. And I can count this area separately from this area. And I can count that second area over here. Well, this length is 3 because it's shared. That length of 3 is shared between the a and 2, or this groups of 3 is talking about both the a and the 2. So when we talk about things in terms of groups, it seems consistent. When we talk about things in terms of length and width, it is also consistent, and we can see they actually mean the same thing. I'm just going to do 3 groups of 2, and I'm going to add that on because these are not like terms. I can't combine them. This is still counting a's, this is still counting ones, and I can see that those 2 areas combine with addition. So this thing is something that we can do. We can actually show that we can get rid of these brackets using what we call distribution. When I use algebra tiles, it's really the same thing. If I want to multiply 2 times 3x plus 1, we have to remember that the 2 represents the length. Whenever we have multiplication, one part is length times the other part is width. So if I have two things being multiplied, I should be able to express this with a length and a width. The area, which is going to give me tiles, remember when I multiply length times width I get area. Algebra tiles represent area. I can see that I have 3 x's along the edge plus 1 along the edge. I have 2 1's along this edge, or two groups of 3x plus 1. Well, if I have two groups of 3x plus 1, I have 3x plus 1, 3x plus 1. That's going to give me 6x plus 2. And again, I could show this using this distribution. I can say that I have two groups of 3x. Well, that's going to be this group of two groups of 3x, or 2 times 3x. I'm just going to highlight that. So this is two groups of 3. X is going to give me 6x. And then I have also two groups of 1. Well, that's going to give me these 1's here. That's going to give me 2 1's. Or 2 times 3x is 6x. 2 times 1 is 2. And it's consistent with my area model. It's consistent with my algebra tile model. It's consistent with my how I understand in terms of groups of things. When I talk about two groups of 3x plus 1, I should have 6 x's and 2 1's. So this length times width, whenever we have two things being multiplied, we can express it as area. And if we're dealing with algebraic pieces, we can show them with algebra tiles as well. And again, the algebra tiles represents the 3x plus 1 algebra, or sorry, the 6x plus 2 algebra tiles is going to represent the areas of 6 x's plus 2 1's. Remember, the algebra tiles represent area, so then we have to make sure we understand what the length and width parts of that expression are.